In this video, we will talk about how to count the number of elements in disjoint sets. So disjoint sets are when two sets have no overlap. There are no elements that are common to them. So we will explain how to do this using an example involving a deck of cards. So I want to do a brief overview of how decks of cards work in case you're not familiar with them. So I'm going to let you be a universal set, and it's going to be the set of cards in a standard 52 card deck. All right, and in a standard 52 card deck, there are 4 what are called suits. So the suits in a deck of cards are diamonds, hearts, spades, and clubs. So each of these 52 cards has one of these 4 suits. And there's an equal number of each suit. So if I do a quick division, if I did 52 and I divided it by 4, I end up getting 13. So that means there are 13 cards in each suit. So there's 13 diamonds, 13 hearts, 13 spades, and 13 clubs. Okay, and within each of those 4 suits, there are 13 cards we now know, but they are distinguished by their rank. So there are 13 ranks in each suit. And the ranks are A, or that's sometimes called an ace, a 2, a 3, 4, 5, 6, 7, 8, 9, 10. And then there's a jack, which I'll label as J, a queen, which I'll label as Q, and a king, which I'll label with a K. And the jack, the queen, and the king, these are called the face cards. So each of these 4 suits has these 13 ranks. So for example, among the diamonds, you would see an ace of diamonds, a 2 of diamonds, a 3 of diamonds, and so on, up until a queen of diamonds and a king of diamonds. Alrighty, and that's true for all of these 4 suits. So I'm going to put this in a little bubble. So a little bubble here, a little thought bubble. Okay, and I'm going to introduce a definition. So I'm going to let n of A, which I write as n parentheses A, this is going to represent the number of elements in the set A, where A is a set with finitely many elements. So in our class, all the sets that we're going to be focusing on and trying to count the number of elements in are going to be sets that have a finite number of elements. And one more time, so with this notation, this n parentheses A, the way I say this is we say n of A. So this is a function technically, and the way we say function notation in words is we usually say stuff like f of x. So in this way, similarly, we would say n of A. All right, let's look at an example. So example 4 says the following. In a standard deck of 52 cards, how many cards are a 3 or a 7? Okay, so there's sort of 2 groups here. There are the threes, and there are the 7. So I'm going to introduce some set notation. I'm going to let W be the set of 3s, and I'm going to let C be the set of 7s in this standard deck of 52, but it doesn't really matter what I call them. So if I wanted to call the first set A and the second set B, that's fine, but I just want to call them something. So one thing to notice about these, so if we draw these 2 sets with circles in a Venn diagram, so if I let W be this circle, this is the set of 3s, and then if I draw a circle for the set of 7s, those 2 circles have no overlap. So this is C. This is the set of 7s. Because there's no card in the deck that's both a 3 or a 7. You can't be both numbers at the same time. So these two circles are disjoint. These sets are disjoint. There's no elements in common. And I can see that visually, there's no overlap. All right, so W and C here, they are disjoint. So our goal in this question is we want to count the number of cards in a certain set. So I'm going to use my notation, n of something. And our goal is to count the number of cards in, because it says the number of cards that are a 3 or a 7. Seeing the word or makes me think of union. So we need to count the number of cards in W union C. All right. All right, so that's going to bring me to our first key fact in this video, which is when two sets like W and C are disjoint, then the number of cards in the union of those two sets, the number of elements in the union of those two sets, is just the number of elements in the first set, W, plus the number of elements in the second set, C. So in other words, in our example, we just got to count the number of 3s and then add that to the number of 7s. All right, so let's write that down. So in this example, the number of 3s or 7s, which is what the question wants us to find, is equal to n of W union C, the number of cards in the union. And base the number of cards in W plus the number of cards in C. I can say that those two things are equal because of the fact that we stated above. These two sets are disjoint. Okay, so n of W is the number of elements in W. So this is the number of, W is the set of 3s, so this is the number of 3s. And n of C is the number of 7s. So in a deck of 52 cards, how many 3s are there? Well, there's 1 in each suit, and there's 4 suits, so there's 4 3s. Same thing with 7s, there's 1 in each suit, so there's 4 7s, and 4 plus 4, that is 8. And that's our answer. That's how many cards in a standard deck of 52 are either 3s or 7s. So if you've seen, if you're familiar with the standard deck of cards, this may have been an easy example for you, but it still helps for us to establish this framework of this fact for counting the number of elements in a union when our sets are disjoint, because it's going to help to have this when we get to more complicated examples. So we can get more general than this. So I can get more general if I have x1, x2, comma, dot, 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 up to xk, all being sets, such that any two of them have no common elements. And if that's the case, we call them pairwise disjoint. So now we could have more than just two sets. And if I do have more than just two sets, and if I look at any two of them, if they have no common elements, we call the collective set pairwise disjoint. So what's an example? So using the previous examples framework, if W is the set of 3s in a deck of cards, and C is the set of 7s in a deck, let me just say in parentheses here, in a deck of cards, in a standard deck of cards. And then let's do one more, a third set. Let's say that this is the set of face cards in a deck. So all the jacks, all the jacks, queens, and kings. These three sets, it turns out, are pairwise disjoint. These are pairwise disjoint. If you look at any two of them, they don't have any overlap. In fact, if I scooch that little bit of notation there down, if I draw a picture here, If I were to draw circles for W and C, they have no overlap. There's no common elements. There's no cards that are both 3s and 7s. And then if I draw the circle for O, that has no overlap with W, and it has no overlap with C. So there is no overlap, which means these are pairwise disjoint. Okay, so if that is the case, if you have sets like this that are pairwise disjoint, and you want to count the number of elements in the collective union of all of them, x1, union x2, union ... up until the union of the last set, this equals, I think, what we'd expect. It's the number of elements in the first set plus the number of elements in the second set, x2, plus ... and you keep going until the number of elements in the last set, which I'm calling x sub k. Whatever k happens to be. Okay, and just like before, with two sets, this is only true if the sets x1, x2, xk are pairwise disjoint. And visually, that means there's no overlap between any of them. All right, so that is a generalization of the previous fact that we had. So the question that I want to end this video and leave for you to think about before our next lecture is, what is the number of elements in a union if W and C, our two sets, are not disjoint? So if they do have overlap, if there are some elements that are in both of them. And the answer to this question we will talk about in our next section, 1.3. So in terms of our goals for the section, we finished our last goal, which is talking about how to count the number of elements in a disjoint union of sets. Counting the number of elements in a Cartesian product, we actually won't talk about in the lecture videos, like I mentioned in our overview, because we saw this briefly in section 1.1. So you're actually ready to tackle these already on the homework.